Human Mimics. In this particular example, the picture on the top right is designed to mimic a hand of a human being in order to do writing. And the pictures on the bottom, it's to type on a computer keyboard. Now, the reason we do that is because there are times that we need the robots to do these things for us in case a human being cannot do that. The keyboard is a station that has X and Y coordinates for each key. And when we place the keyboard in a 0, position, knowing its reference point, knowing the reference point of the robot, and program a combination of letters, it's relatively speaking easy to go for the robot on the tip of the finger and hit a key, meaning that go to a particular X and Y coordinate, hit it and come back. Or go from one coordinate to another coordinate to create a word. That's normally a very simple process. But in order to have this process very precisely done, these fingers need to be very detailed control. So we have 16 different servo motors for each part of each finger in the hand. 3 motors for the wrist motion. So here we have a large number of degrees of freedom to be able to simulate the hand, to be able to hit a key, or to be able to hold a pen in order to write. Now, writing is something a little bit slightly different than hitting a key, because writing is changing the orientation of the gripper, pitch, roll, yaw, as opposed to hitting a keyboard. The orientation of the gripper does not change. Only the sub arms change, but the orientation is the same. We talked about the wires. They are a set of actuators which basically are computer-controlled screwdriver motors and gears with optical encoders. Because we want very fine movement of every single part of every single finger, we have to have screwdriver motors, meaning that as the motor rotates, the screwdriver goes out and in very finely in order to have the wire being pulled or pushed very finely, so the movement will be a very fine movement according to just to imitate a human being. So there's a large group of actuators and number of sensors like pressure sensor, load cells, proximity, tactile, inertia, tilt, to basically provide the controller with the data that it needs to do to direct the fingers what to do next, just as we human beings do. Anthropomimic robot. That's a robot which looks like very close, looks like a human being. It also mimics human reflexes. It generating artificial reflex. It cannot interpret what is pain, for example, but it knows, according to some sensors, it knows what should be the position of the action of the part, so actually it will be interpreted as a pain. Now, there are 2 high-definition cameras with field programmable gate arrays that have overlap, and they actually mimic 2 eyes of the human being. And then also 2 microphones that imitate the sounds of a human being. And they simultaneously directional and acoustical audio characteristic read by human ears. The bandwidth of the frequencies of us human being here can be generated by 2 microphones. 1 microphone is not enough, just to have a very similar sound going into our ears. Having a combination of a set of two microphones will imitate the sound of the robot as if it was a human being. Interesting about human mimics in terms of tactile robot fingers. It is basically the type of fingers in order to sense what we are holding, what the robot is holding. Sometimes the finger's touch is more sensitive than a human touch, just because the resolution, just because the level of sensitivity can be controlled by specific sensors. Now let's look at the particular tip of the finger, particular touch sensor, what you call. There's a finger-size biotac sensor, which is made up of soft, flexible skin cover with a liquid filling. In the picture on the left, the entire volume is filled with liquid. And the plastic covering is a very flexible and soft skin cover. Now, as the sensor slides over a surface, it is able to vibrate in characteristic ways because it has kind of a fingerprint. The vibrations are then detected via hydrophone microphone located within the sensor's bone-like core. So because of the fingerprint itself on the surface of the flexible skin cover, as we go along, there will be vibrations that they will be interpreted just as we humans do. And some researches were done that concluded that for some applications, 4 fingers are sufficient to do many tasks. In fact, the majority of the tasks can be accomplished using only 4 fingers and not 5. One of the fingers is acting as an opposable thumb, and we can see the finger on the bottom. So 3 and 1 can do the work in most of the applications. The applications are remote diffusion of improvised explosive devices. Just holding this device and put it in a safe place, doing dangerous task. Fruit and vegetation hardness testing. Taking this apple, putting a pressure on the apple, 4 fingers will do. Having pressure sensing, understanding the hardness of the apple, the quality parameters of that particular apple to make decisions whether to put it in the green box or the red box, for example. Egg packaging. When eggs coming randomly, and we need to package them and put them in a carton in a very well pre-programmed positions and orientations, but they come randomly, these 4 fingers will pick up the head, change the orientation again of the gripper, and we locate them, place them in the XY coordinate of these cartons of box of eggs. Fruits and vegetation sizing. We talked about the displacement of the fingers before. Now, these displacements will tell us exactly what is the size of that particular fruit. We put additional pressure to understand what is the quality, not only the size, the quality. Can include some sensors to sense how much juice there is inside the fruit to know whether it's good to be picked up, good for juice, or good for any kind of other food.